All right, thanks very much for inviting me to come. It's really been a lot of fun. And today I'm going to talk about two subjects. First, our proposal that you should understand the quantum computational complexity of complicated conformal field theory in terms of a quantity called the action, which I'll tell you what that is, for those who don't know about gravity. And then also I'm going to talk about, in the spirit of this workshop, bounds, possible conjectured bounds, nothing is proven, but conjectured bounds on the rate at which complexity can grow in the local system. And one paper is out already, a sort of short summary paper. There are hopefully many more to come. And I should thank my really great collaborators, Adam, who's in the back, Dan Roberts at MIT, Lenny in the front here, and Ying, who's Lenny's graduate student. They're all very great people, and we've had really a lot of fun working on this. So, let's start off with things black holes do well. Here's a black hole. It has a radius r, so I'm thinking about flat space so far. And we know from Bekenstein that this black hole has an entropy. And its entropy is proportional to its area in Planck units. That's what this formula says. What's funny?
Isn't the diameter r in
Yes, you're right. You're right.
You're right, Brian. You're really great collaborators.
They keep you honest. They keep you honest. Right. Okay.
So it's all wrong.
Yeah. Sorry, guys. There we go.
Well, we've been having trouble getting the order 1 constants anyway.
Right. One of the messages of this talk is that it takes 5 very smart people to get the order 1 number right, and even then it's not completely clear. So, okay. So first thing black holes are good at is they're the densest memories in nature, and the proof of this is this: that you imagine they have a more dense memory, but then it just collapses to form a black hole. That's it, right? There's nothing you can do. So you just get cut off here. So there's already some indication, even from the very early days, that they did something, in a fundamentally impossible to beat way. Okay, now we can also ask about dynamics. So here's my black hole when I kicked it with a sizable perturbation. And you can ask various questions. You can ask, what's the time for this black hole to relax to macroscopic equilibrium? So for the sort of autocorrelation functions to decay, and then also more macroscopically in terms of the internal dynamics of this thing. What are these e to the s states doing in time? And so there's actually 2 time scales. The first is the local equilibrium time, which is called TD, T sub t. And just on dimensional grounds, it has to be proportional to the radius of the hole in flat space. There's no other scale. But if you use Hawking's formula for the temperature, you can convert this into this h bar over t that we've been seeing so much of in this conference. And then more recently, it was pointed out that if you want to ask about the dynamics of quantum information in this case, then you get other interesting time scale. This is the scrambling time, which Douglas talked about this morning. And here you see the sort of prefactor, this 1 over t, but also there's a log s. So this is longer, but at the same time, not as long as it takes for the black hole to evaporate. Right? So there's still something interesting happening on these intermediate time scales. And so then Sakino and Susskind conjecture that black holes are the fastest scramblers, meaning they do whatever this thing is as fast as possible. And the proof, just evolve backwards in time, 5 hours, and listen to Douglas's talk. Okay. So this is also true. So not only do they store information as sort of densely as possible, they also process it very rapidly. And so we have these many states. The system is undergoing some dynamics. And in this talk, we're going to think about what is the complexity of this state. So here's my time-evolving state. And the complexity is just how many simple elementary operations you need to do to produce this state from something simple. So this talk is going to all be about the complexity. And yeah.
What's the definition of something simple?
I'll come to that in a second. I'm being a little vague here. And so our conjecture is that the black holes are the fastest complexifiers. And we had a proof, but it rapidly became too complicated to put in this talk. So that's what I'm going to talk about today. In particular, I'm going to defend two proposals. The first is that you can calculate the complexity of the dual state using an action, which is this A sub w of a certain region in space-time. And I've chosen some conventional normalization here, which I'll explain a little bit later. And we call this complexity equals action, or CA duality. And the second proposal that I'll defend is that black holes increase their complexity as fast as possible. So everyone understand what I'm gonna talk about?
Well, I don't quite understand number two. Is it impossible for a black hole to be in a steady state where its complexity is not changing at all? Or it computes as things interact with it? Maybe.
It's not possible. So the black hole, I mean, as far as we understand, black holes formed from collapse are highly dynamical objects that even after they settle down to what appears classically to be a steady state are still doing something internally.
I know they're
long
radiating and
after.
things like that, but okay.
Yes.
I don't understand how they increase their complexity in that process later on. Okay.
Yeah, well, okay, just wait a little while and we'll see. Okay. And we're going to use ADS-CFT just to have a very concrete setting. So I'm going to take my flat space black hole and put it inside this ADS box. And although the scaling with the size of the black hole is a little bit different, they're still the same local equilibration time, which is 1/T, and the same scrambling time. So in terms of the temperature and the entropy, these times remain essentially the same. And so here's the precise object we're going to consider. It's a system consisting of two conformal field theories, one on the left over here and one on the right. And these conformal field theories don't talk to each other, they're not coupled in any way, but they can be entangled. And so this space-time, which describes this outside region, which is one field theory, this outside region, which is the other field theory, describes an entangled state between these two conformal field theories.
Sorry, but then this black hole is really in a static state. There's no increase of complexity.
No, that's not, no. Why do you say that?
Because
I don't understand. Your question, you can't answer that question.
you said
This,
Are you going to describe the calculation?
Yeah.
Okay.
Let him
So
go on
let's
a
let
little
him
bit.
go.
yeah, I'm going to evolve forward on both times, right? So the phases don't cancel out.
okay.
Right? If you evolve, this way, then it's a steady state.
Yeah.
But if you evolve, if you evolve forward, then it's the same. Then it's dynamic. Okay. Yeah. So I just want to set up this picture for people who don't think with these pictures all the time, right? So you have time running up this way, roughly speaking, on the left and right, and we can control them independently. You have these horizons here, and this is the reason why you can tell that the right CFT can't affect the left, because if it sends information in, it never can get past this blue dashed line, so they can't talk to each other. They can meet in the middle, perhaps, but they can't directly affect the other. And then this is what we call the radial direction, the holographic direction. And the meaning of this picture is it's a conformal diagram, so light rays travel at 45 degrees, but distances are not necessarily represented accurately. And here's the picture of something growing in this state. So what's changing in time? If you look at this initial surface here at t equals 0, and you draw the spatial geometry, what you find is that it looks like you have so at each point on this diagram, there's a suppressed sphere of some type, a one-dimensional line or a two-sphere or a three-sphere, depending on the dimensionality of the system. And as you go across the radial direction here, your sphere shrinks a little bit. This is the horizon of the black hole, and then it starts getting bigger again on the other side. So this is literally a wormhole from the left to the right, which at t equals 0 is some fixed size spatial value. Right. Now, as you go up in time, on the left and the right, so you're going forward on both sides at the same time, this interior region gets bigger. So that's the sense in which this spacetime is not static, right? And that answers, that's sort of the first glimmer you have, Joel, of what's going on. There's something outside, it looks like it's in equilibrium, but inside something dynamical is happening. And we're going to associate this growing dynamical interior with this complexity growth in the black hole. Yeah.
So it gets longer. Right?
Yeah.
It gets thinner in the other two directions.
No, it doesn't. The thickness here is always of order of the ADS radius for the large black hole.
Oh, sorry, I read that.
Yeah. So this picture is actually fairly accurate. It just comes in and then gets longer linearly with time. Okay, so the question that was asked by various people, including Lenny and Hartman and Maltasena, was what is dual to the growth of this black hole interior? And the suggestion was that it's the complexity of the holographic state, this thing that I defined at the beginning about how hard it is or how many elementary operations you need to perform to construct a state at some time t from a simple reference state. And so this is really the state of the system. It's an entangled state between the left and the right. These E's of L and R are the energy levels of the left and right system. And they're entangled with this peculiar weight. And the point of this weight is that if you trace over the left or the right, you get the thermal state on just the other copy. Right? So this is a purification of the Gibbs ensemble. And what I mean by this schematic e to the minus IHT is I evolve forward in time on both the left and the right. So this state gets phase factors, e to the 2I ET. Like this. And so it's not static, it changes in time. And when you trace out one of the sides, this phase factor goes away. But if you look at the interior dynamics, something is happening. And the rough field theory expectation for how rapidly the complexity grows is to first say that it should be extensive in the number of degrees of freedom. So that's the entropy here. You sort of have some number of active degrees of freedom participating in the dynamics. That's roughly the entropy. And then as we saw before with a black hole, the sort of characteristic time scale is the temperature, 1 over the temperature. And so the idea would be that each of your S degrees of freedom has some elementary operation happening roughly every 1 over temperature seconds. And so this is how the complexity should grow. And so our proposal is the following. We introduce a space-time region called the Wheeler-DeWitt patch, which is defined as follows. You fix your boundary time on the left and your boundary time on the right. Here I've taken them to be equal, but you could do something different. You shoot out light rays backwards and forwards and terminate them when they meet or when they hit the singularity, etc. And this is defined some space-time region. And the meaning of this region is it's the union of all of the space-like surfaces that pass between the left and the right. So, this is one space-like surface. There's another wiggly one. There's this one I showed you before. It's the union of all those choices. So it's something which you should naturally associate with the state of the boundary at these 2 boundary times. And our proposal is that the complexity of the boundary state, which I haven't defined precisely yet, but I'll talk about in a second, is just equal to the action of this region in space-time in units of pi h bar. Okay. That's what this formula says. So that's our proposal. And by the action, what I really mean is just the usual thing that we all talk about. Here's the Einstein-Hilbert term. This is the curvature of space-time. That's the cosmological constant. There's Newton's constant. You have, again, Newton's constant here. This is a surface term, which you have to put into the action for it to make sense. And this is the extrinsic curvature on this boundary. So this is like the purely gravitational part. You can also consider electromagnetism, and we'll do that a little bit later. In that case, you'd have F squared. So this is the field strength tensor. Some term in the action like this. And so the proposal is literally just take this region, you have a solution, calculate the action, and that's supposed to be the complexity.
May I ask you?
Yeah.
Usually when you have an action like that and you compute the value of the action on equations of motion, you typically get area of the horizon proportional. The action is proportional to the entropy and area of the horizon.
You mean like Euclidean action?
Yeah.
Yeah, so this is Lorentzian action.
Okay, so what exactly you compute then?
We compute.
The value of the action on equations of motion?
Yes, we have a solution. So we have a solution.
Mm-hmm.
We form this space-time region in real time,
Mm-hmm.
and we compute this Lorentzian action evaluated on that solution.
So here it's called W, and on the next thing it's called M, is that correct?
This is to indicate that I can do this for any region M. So later I'll use
The region
this.
you want to do is W.
Yeah,
Yeah.
yeah. But, yeah, you'll see. Sorry for the confusion. So I just take the solution one more time, take the classical solution, form this space-time region, take my fields, evaluate the classical action in Lorentzian signature, and that's supposed to be the complexity.
And you would do this no matter what the bulk solution is. So that
Yes.
evaluates the complexity on any field theory that has a gravity dual for any, in any state.
Well, okay, there's some assumption here about semi-classicality and that the action makes sense and so forth, but yeah, that's right, any state of the field theory.
So does the M have to be defined between two Cauchy surfaces, or something like a causal diamond? I don't know.
Let me say, yes, that's the basic idea, but maybe there's an extension where you don't have to do that, but that's the basic idea.
Wait, let me ask something again, because I thought in principle you only need one CFT, you would still make the same projection.
That's right.
You could still define this W to be the set of points that are
Yeah.
space-like related to your boundary
Yeah.
size.
Yeah, you could do it with just one copy.
So, just following up on that, so
Yeah.
W as defined is effectively the entanglement wedge of the, as we defined it for the union of the two Cauchy slices?
I mean, it's the entire Cauchy surface.
Yeah, I understand, but it's the entire Cauchy surface for both boundaries, so I think what you have is the entanglement wedge.
But then that would have domain of dependence of each one going
Yeah.
on the entire
Oh,
boundary.
because of
so
the
the
boundary.
entanglement wedge would be-
It's more or less the opposite of your.
But it's a quantity that's constructed from the boundary
Yeah.
rather than from the
Yeah.
bulk.
That's right, that's right.
Constructed, you should
It's
be
really,
able to
this
from the
boundary anchoring seems to be conceptually important, whether you can go beyond that is not completely clear to us.
So it's more like a complement of causal wedges.
Okay.
Yeah.
Yeah, I guess that's right. All right. And, right. So that's the proposal, and now I want to go through it in a little bit more detail and try to motivate this, and then we'll talk about the bounds. Okay. So let's stop for a minute and think about the ground state again. So here's now time on the boundary. I don't have to have two copies anymore. I can just have one side because it's the ground state. There's no entanglements. This is the CFT space direction, which I was previously suppressing on that diagram. Here's the radial direction again, and this is empty ADS space. And some years ago, I proposed that you could think about this space-time, or at least the space, at 0 time as being associated with a tensor network, which did the job of constructing the state of the conformal field theory from a simple state, from a product state with no entanglement. So here's kind of the tensor network superimposed on the geometry, and this is what you should have in the back of your mind. At least that was the proposal for how to think about the ground state of this conformal field theory in terms of the holographic geometry. Okay. Now we can ask a question, how big are these tensors? How much space does each node in this network take up? And where should I think about these nodes living? And it was argued originally that you should think about these nodes as being roughly of order the ADS radius in size, like little patches of space of order the ADS radius. But I would like to suggest that we should be a little more democratic and not think of them as just living at a single time, but let's let them spread out a little bit in space-time, right? Why should we stick them to one Cauchy slice? We could let them sort of sit anywhere. And so if I take the principle that these tensors should occupy one ADS sort of distance in every direction, then the causal patch appears pretty naturally, this weird to width patch, because the proper time as you go out between these two light rays is always of order the ADS radius in this standard, ADS, empty ADS geometry. And so maybe I should really think of the tensors as living kind of everywhere in this wedge, right? And in that sense, what is the tensor network telling me? It's telling me how to prepare my state from something simple, from unentangled states. And the number of tensors would be a measure of the complexity, and so maybe it's not crazy to associate something which depends on this whole wedge with the complexity of the number of tensors in it. So just the logic again, I have a state, my conformal field theory, the ground state. I can represent it as a tensor network. This tensor network is like a record of the computation which prepares this state from something simple. I want to argue on general grounds that I should associate those tensors with an ADS radius sized chunk of space and maybe space-time, and in that picture, a very natural thing to consider is these expanding light rays. Okay, so I should associate the tensor network with everything, and then some property of this region in space-time would calculate how many tensors are in my network, or the complexity of the state. Now, what about this wormhole picture? So there it's a little more complicated. There are more moving parts. Here was my outside region for the left, my outside region for the right, and the wormhole part. And so now I would have something similar to the ground state network on the outside. This is like a, you see I'm going from 2 to 1, from 2 to 1. So it's like a normalization group network on the outside. And I have one of these for each side, except that I'm going to cut them off somewhere on this blue line. That's like the horizon, this blue line here. And then I have a second part to the network, which is the interior part. And this interior part is it's more like flat space. You don't have this hierarchical structure. You have just rows of tensors of the same number in each step. And this was first suggested by Hartman and Maldacena. And so the idea is I sort of have the RG part outside here, that's this red bit. Then I have some kind of wormhole network, which tells me how to prepare the entangled state between the two sides. And then I have another RG part on the right, which prepares the outside state. Okay. And so from this perspective, I have a tensor network for the interior as well. And as was asked earlier, the sort of how much you can ask, what's the space-time volume of this tube? And it's long. Its cross-section is roughly the area of the horizon, and its length and time is essentially the ADS radius. And so it looks like I have just enough room to put one tensor everywhere in this space-time volume.
Sorry.
One tensor per ADS radius.
That's right, one tensor per ADS radius.
I'm a little confused about which time I should use here. Like if you go back to this geometry, the black hole geometry.
This one.
Yeah. So when you say the time is about the ADS radius.
Yeah.
Time.
Well, here I'm just as a simple estimate, just looking at the time from the horizon to the singularity with no motion in the other direction. So inside the horizon, the radial coordinate is time, and so I just go from the horizon to the singularity, and that takes an ADS radius, an ADS time.
Proper time?
Oh,
Proper time?
Yes, proper time.
So in this tensor network renormalization construction of the Euclidean path integral,
Yes.
there's a similar picture where you have the state coming outside, which is the usual tensor network.
Yeah.
And then there's some intertwiner that glues together the states to give you the thermal density matrix. What you're proposing here is sort of how to evolve that intertwiner up to grow this complex.
Yeah, exactly. Yeah, I'll have an explicit figure about that a little bit later. Yeah, sure.
So your original motivation for these networks was back to the Buteyko-Yanagi formula, right?
That's right.
And there also the geometry of space was associated with the network, but it wasn't a fixed time slice. So it seems like if I was to apply this logic to the entanglement entry now, I wouldn't want to go with Buteyko-Yanagi. I want to go with something that's also spread out over this diamond. So you want to say that the network grows space. But in the Buteyko-Yanagi case, we know that it's a slice of space, not a volume of space. And now you want to say the same thing, but that you want to associate with the volume.
Well, yeah, so it's a little unclear what exactly you want to do, like whether there's an ensemble of equivalent networks that I should associate with the space-time region, and any particular choice is associated with some slice. So like every equivalent network will give you the same entropy, but perhaps there's a sense in which there's a right slice to look at if you want to calculate the entanglement geometrically, like just by counting bonds. Does that sort of make sense? Like I could add extra links that don't do anything. That might correspond to having some wiggly slice, and that's just saying I shouldn't have those. I should look at the minimal, some like minimal slice, and then that's where the entropy is as simple in terms of the structure of the network.
There better be some compatibility between the entanglement and the geometric picture of entanglement and the complexity.
I completely agree, yeah. So at the level I've said here, it's too vague to have any actual conflict, but I agree in principle that's a concern. Yeah?
Well, you motivated this region, the Wheeler-DeWitt patch, by saying, well, you could have fitted any sort of space-like slice
Yes.
and put the tensor network on that. But then, if you say those words, what is the motivation for summing over that? For integrating that region?
I don't, this is, what is?
Ultimately your complexity, the equal sign, the action is sort of
Yes.
integrating that whole region, but your motivation doesn't somehow match onto that.
No, I think if you say that where the tensor lives is not at a definite space, then it's not, Yeah,
I mean, you might have some over it with some measure or almost like.
Yeah.
Or take transport, but it's.
I think
not-
the short answer is I don't know. I don't know. It's a great question, and it's just not completely clear how to make this picture, in terms of space versus where exactly it's living. Lenny, do you want to say something?
You could ask two questions. One is, what is the motivation? The other question you could ask is, what is it that motivated us?
Yes.
When you're finished, I could take 2 minutes and just say exactly what motivated us when you're finished. I don't want to interrupt.
No, that's fine. I think, I may say some similar things to what.
Oh, okay, then.
I was just trying to give a sort of tensor network picture of this, but let's not get hung up on it too much. Okay. So here it is. Okay, Lenny will be happy now. So starting from this picture of Hartman and Maldacena where they drew this tensor network, I guess Lenny suggested that maybe we should really think about the volume or the length of the volume of the wormhole as calculating the complexity of the state. It's just counting how many tensors there are in this tensor network, and they're called, this tensor network is growing as I time evolve the state. Now, that led to a formula like this, which said the complexity was like the wormhole volume in units of Newton's constant and some length scale L here, which had to be chosen. And if you choose this length scale to be the ADS radius, for example, for a big ADS black hole, you get the formula that we had before, that the complexity grows proportional to the temperature and the entropy. Now, a slightly unsatisfactory part of this formula is that you have to choose this scale to fit the problem to some extent. So if you look at a small black hole, then you have to choose the ADS radius to get the Schwarzschild radius to get TS. And if you look at charged black holes, it's even more complicated. So one of our main motivations going into this was to try to understand how to take this formula and extend it so we don't have to make these choices anymore. And you see, that's what the action does. In the action, there's no length. It's very naturally a dimensionless quantity in units of h bar, which is associated with this patch. And so the idea would be that these length scales effectively come out in the calculation without putting in any information by hand. And now let's talk a little bit more about what the complexity is. What is this formula supposed to tell me? So like I said, the complexity is the minimum number of elementary operations you need to produce this state from a reference. And so you need 3 pieces of information. You need the reference state, which is talked about here. So you can imagine starting from either a product state, or you could start from, for example, the thermal field double state at t equals 0 and ask how hard is it to produce the time involved state from that state at t equals 0 as a function of time. You need to tell me what the elementary operations are. That means you have to tell me what the universal gate set. So this means a set of unitary transformations that are simple, which can reach everywhere in Hilbert space or close to it. And what I'm essentially going to do is count the number of gates that I need to apply from this elementary set. That's the complexity. And you need to really be precise, you need a tolerance parameter, which tells you that you're allowed to not quite hit the state you want, but make a small error as long as it's not too big. This is important because if, for example, you had a gate set which was discrete, then the unitary group is continuous, you can't possibly hit every state. So you need to, allow yourself a little wiggle room. But this will play no role in our discussion. And so with these 3 requirements, there's a lot of ambiguity in the complexity. Part of our motivation is to try to cut through some of this ambiguity, to find a way to normalize it or to give meaning to it in precise terms. But I should emphasize that the rough features, the growth with time, the extensivity, all this kind of stuff is independent of the detailed choices here. Okay. So what you should really think about for the rest of the talk is that we're taking our reference state to be the thermal field double state. And the gate set is something which you should think of as like a limit of infinitesimal gates. This is sort of based on the ideas of Nielsen, where you define complexity as some kind of geodesic distance on the tangent space of the unitary group. And so then you would think of the complexity as something like I have gates which are close to identity with some factor of delta. This H is like a simple generator. It's a simple operation that affects only a few degrees of freedom at a time. And the complexity would then roughly be the limit as delta goes to 0 of the number of gates times this little parameter delta. Yeah.
And in the bulk, that single delta n is something that goes by an ADS somehow volume?
Um,
If you tie it back to the, well, sorry, maybe this is.
None of this is bulk idea.
Yeah, this is just, I'm just trying to define, or, you know, give you a rough idea.
Yes, that's my question when you get to.
Yeah, okay, yeah. So this is not a full definition, but we're speculating that there is a way in the continuum, perhaps, to make this really a sharp definition, and that this, up to some constant proportionality, which we can try to fix, should be thought of as the left-hand side of complexity equals action. So then this is the full proposal. The complexity, as defined on the previous slide, roughly speaking, is just equal to the action of this patch. Again, this is the standard gravitational action, and there's some normalization which we fixed by matching with some previous ideas, which I'll mention in a little bit.
In the continuum,
Yeah.
the simple unitaries would be things which are just integrals of local operators of some kind.
Presumably,
Like
yes.
exponentials of integrals of local operators.
Yeah, the infinitesimal elements would be products of few fields integrated over space. Yeah.
So, okay, so now let me ask, so on the,
Okay.
in the bulk, this single gate would be, what? Is there a better understanding?
I don't have a really good answer to that question. I mean, like I said, we don't really know where the tensors are living, if they live anywhere. So I mean, you know, we can of course just, you know, say what chunk of space-time corresponds to increasing the complexity by 1 unit. But not sure how much insight we gain from doing that calculation.
But one is somehow supposed to think of it as some bit of time evolution within bulk.
Yeah, I mean, I think it's especially clear with this wormhole thing, with the wormhole growth. You know, there's like a little piece you've added, and that's where the tensors live, roughly speaking, in that little chunk of space-time.
So since in this Wheeler-DeWitt case, the time evolution is a gauge transformation, so I think this gauge transformation correspond to, in this tensor network, you do some modification of the tensors without changing the state.
That's definitely a very plausible guess in my opinion.
But then there are many ways to do them. So it's
right, but there are many ways to form this thing. Yeah. I think that's a great guess. It would be really nice if there was.
What was it again?
So in a tensor network, you know, you can add and remove tensors or change tensors in a way that doesn't change the state.
Yeah.
So the guess would be, or one very good guess is that this freedom in the tensor network side is associated with the same kind of freedom you have here to choose any Cauchy surface you like. I mean,
well, basically it corresponds to diffeomorphism, and some part of the diffeomorphism is the time evolution.
Yeah, I think this is a good guess, but I don't know a way to test this guess. So that's the status.
What is the simple state?
Well, for our purposes, we'll take it to be the thermofield double. And what that amounts to here is actually subtracting off this part outside the horizon. Because of the boost invariance, it doesn't change with time. So it's UV divergent, but we just remove it, just subtract it. And that, I think, roughly corresponds to saying that you're referring not to the unentangled state, but to the thermofield double.
But if you wanted this conjecture to apply more generally to CFTs with bulk tools, you wouldn't want to do that.
No, absolutely.
You'd want to pick a different simple state.
Yes, so you can, for example, take an unentangled state. And then this, well, I'll come to this at the very end, but the action is UV divergent. And it roughly matches our expectations for how complex the conformal field theory ground state would be.
Well, I don't quite understand why you would use the ground state as a simple state, since you already need a huge tensor network.
No. Sorry, I'm asking what is the complexity of the ground state in terms of an unentangled state.
So by unentangled, good, you mean really you disentangle all the...
Yeah, like think about the state with a very, very large mass gap. And I want to ask how do I really build all the long-range correlations from that very, very short-range correlated state. So absolutely, we believe that the action, I mean, it gives an answer which is consistent, very roughly, with the counting. But, yeah, there's still some questions there.
I'm still puzzled by the fact that you said the simple gates are like local operators in the CFT, because...
Yeah.
I mean, I can see how in the tensor network picture in the bulk, you have gates that are simple and that build up the state that you want.
Yeah.
And you need a longer tensor network. And on the boundary, the evolution is is a time evolution forward from t equals 0, right?
Just wait.
Yeah.
I have a picture just for you.
Great. Just for me?
Just for that question. Okay. Right. And so again, just to reiterate this point, why does this work? It's because the space-time is a long tube. And if you look at this action, for example, this term here is just 1 over the ADS radius squared. So if I multiply and divide by the ADS radius, then I can go from volume times 1 factor of ADS radius in the bottom to the space-time volume up here and 2 factors in the bottom. So it's very naturally just this action, which appears there for the large black hole. Okay, and then I won't talk about this at all, but you can do a lot of shockwave checks. This was done by Douglas and Lenny, and Dan Robertson, Douglas and Lenny, showing that there's a sense in which this network should be thought of as the minimal network. At least it's consistent with that. The parts of the tensor network that are not useful, that don't do anything, cancel out. And so in these shockwave calculations, there are parts of the network that wouldn't change the state at all, and those explicitly, in terms of the geometry, do not appear. That is, the geometry is, let's say, shorter than you would have thought it would be otherwise, because there are parts of the network that cancel out. So it's not just any tensor network, it's really the minimal tensor network, and so it really seems like a good candidate to identify with the complexity. So I'll now turn to bounds and tell you some of our results. And so that thing which really motivated us, based on all these other things that black holes do really well, is could black holes also be the best at computing or processing information in some abstract sense? And again, the picture is roughly that you have some entropy, s degrees of freedom, which are computing at a rate of the temperature. And this seems to, at least we started out thinking this had something to do with Margulis-Levitin theorem, which is a theorem in quantum mechanics that tells you how rapidly a state and its time-evolved version can become orthogonal. We think now that's probably not directly relevant to our considerations, but it started out motivating us. And there's also a bound by a conjecture by Seth Lloyd at MIT which is really partially based on this Margulis-Levitin theorem, that there's some idea that the fastest that you could compute is proportional to the energy you have available to you. Remember we were talking about TS, that was the wormhole growth. Well, TS was roughly the energy, up to some order 1 factor, the energy above the ground state. And so Lloyd had a conjecture that with some slightly not fully defined notion of computation, maybe the maximum rate of computation would be proportional to the energy. And so in our case, we wanted to imagine that there was some bound along these lines, but not for computation, but for this very precise notion of complexity, which is the number of gates. And so we had in mind something like the rate of change of complexity with respect to the time evolution in time is some horrible prefactor, upsilon, which depends on the reference state, on the gate set, on the tolerance parameter, on the k, which is how local the Hamiltonian is. So like if the Hamiltonian consists of only 2 body operators, then k is 2. If it consists of 4 body operators, then k is 4. If it consists of 20 body operators, then k is 20. And as you increase k, you should think that you can make more complexity, right? Because you can act on more degrees of freedom in one go. And so the idea was maybe there's a bound where the rate of growth of complexity is bounded by some constant which depends on a lot of details times the average energy of the state.
So what is psi?
Psi is the state that I'm evolving in time.
Is it initial?
Well, since it's time evolution, the Hamiltonian is conserved, doesn't matter at what time I take it. So here's my intuition, or a simple intuition for what's going on here. Let's decompose the time evolution operator in terms of some diagonal basis. So here U sub h is a big many-body unitary transformation which diagonalizes the Hamiltonian. Little h is just a list of the spectrum, so it's diagonal in a local basis, and then I reverse the diagonalization procedure here. And this big beast here should be a very, very complicated unitary transformation because it maps from the local basis to the energy eigenbasis. And you can imagine, the level spacing in your system is order, maybe e to the minus entropy. So I could prepare this unitary transformation by adiabatically evolving over a time of order e to the entropy. That might be enough to go slower than all the level spacings. And so we have a kind of upper bound for the complexity of this object by saying, it can't involve one convolution for an exponentially long amount of time. It could be perhaps less complex than that, but we think that's probably a good estimate of the complexity of this unitary transformation. It involves order e to the s simple gates. And so then we have a picture where what's happening is if you're at 0 time, this u dagger and u cancel, and you get just identity. And as you evolve in time, there's kind of a dephasing process where the cancellation between these two exponentially complicated unitary transformations is inhibited. It's frustrated as you dephase in the middle here. And so the sort of complexity growth is like a slow revelation of the exponential complexity of this unitary transformation here. That's the idea. Yeah.
Wouldn't that start happening, in that language, you expect that to start happening from the get-go, from initial time? This dephasing starts happening.
It does happen from the initial time. Right? The wormhole starts growing more or less immediately.
But I thought your complexity sort of stays put for a while and then starts growing.
Oh, well, it depends on the detail of the setup, but yeah, there could be like a thermal time or something where it doesn't start growing. But yeah,
But you say that's compatible with
we don't really understand, in one thermal time, that would be like one layer of gates. So I'm not sure we understand the dynamics of the field theory well enough to say what's happening on that short of a scale, but it's not obviously incompatible, in my opinion. And so here, the largest rate is E, total energy. And so maybe this is really what governs the rate at which complexity can appear in your system. So with that, what we want to do is we want to fix this weird upsilon constant. Just forget about it. Let's normalize it somehow by changing the definition of complexity slightly to absorb it. And fix the normalization, this 2 over pi h bar factor, to agree with the Margulis-Levitin theorem and the Lloyd conjecture. And so then our bound, our proposed bound, says the complexity can't develop faster than 2 over pi h bar times the energy of the state relative to the ground state. Okay? Yeah.
So you actually have the factor of 2. You have a numerical fact, precise numerical fact, and this.
It's conventional, but yes, we put a precise factor on it.
Okay, with some independent definition of complexity.
Well, no, that's
No.
yeah. So the main check we have on this right now is this fact that if I fix this factor for one black hole in one dimension in one system, then every black hole in every dimension of any size hits the bound exactly. Right. So that's what this says. I just fix this. I choose this 2 over pi h bar to be some number. I fix it. It doesn't matter. I could choose it to be 100. It's just a constant. Let me fix it, and I choose it so that the black hole in one particular case saturates the bound. Then what I find when I calculate this action growth is that every black hole, every uncharged black hole in any dimension of any size, saturates the same bound without any need to change the constant. So I fix the constant once and for all. I normalize it in some way. Then it seems that all other uncharged black holes hit the bound. So this is one of the main results of our work.
And complexity is being calculated via these tensor network countings?
That's the idea, yes. So yeah, let me emphasize that we can't calculate the complexity on the field theory side for various reasons. One, because it involves a minimization. You have to look at the minimal network. But also because we just don't have enough control over these tensors to precisely estimate it. But so we're sort of conjecturing that there is some notion that makes sense and checking that it's consistent with the dynamics of black holes.
So
Yeah.
here we really just mean static black holes, right? Or you're conjecturing that.
I mean that
any
the two-sided.
But then you can still make dynamical.
Yeah, well, so you can also do black holes formed by collapse, for example, and you find the same
saturation for
yes.
all of those.
Of course, there can be a transient, but yeah.
But if I don't believe, I would still have a non-trivial result even if I don't believe in action equals complexity. Which
That's
is
right.
that you're showing that the action of a certain patch behaves in a certain way.
That's correct.
Which is quite simple.
That's correct.
The mass in particular.
The mass in particular.
Yeah.
And yeah, I mean, yeah, it definitely roughly matches some complexity picture, but yeah, even without that connection, there's a non-trivial result.
Are you gonna drive that for us, or?
Yeah, I'll show you here how to do the calculation. So here's a way to do it, which is pretty nice. Instead of trying to calculate the patch all at once, let's look at the rate of change with the patch. And so what happens first of all is that these outside parts don't count. Like I said before, they're independent of time because of some boost symmetry. So you can forget about them. This part you can throw away. At late times, this part also does not contribute very much. And so what you have to do is look at this little piece here, which is actually not little. It's the same size as everything else. And you have to calculate how much action is produced by this little increment there. So that's why I put M before, because actually what we're going to do is calculate the action of this little patch and not the whole thing at once. It's just a simpler way to do the calculation.
When you say small, in what parameter?
This region here. Sorry, which one?
You said something was small?
Yeah, this part of the action here is small at late times.
As a function of t.
As a function of t.
So this is exact as t goes.
Yeah. There's some you could call it transient behavior or some early time behavior. That's right. So yeah, this is strictly only corrected asymptotically. And
Which typically means 1 or 2 ABS times.
that's right.
What's that in a CFT? What does that mean in a CFT?
Thermal time.
Yeah, thermal time.
Thermal
Yeah.
time.
Yeah, like
Yeah, so of course.
you go 10 thermal times and it'll be within a few percent of the second.
Thermal.
So here's how we do the calculation. You have to integrate this bulk part of the action over this little gray region there. And then there are 4 surface contributions, 1 from the horizon, 1 from the singularity, and 2 from these light-like boundaries of the expanding patch. And then there are also corners you have to worry about. So there are 4 corners. Now a nice thing about this setup is that the corners actually cancel with some way of regulating what you mean by the extrinsic curvature of the corner. So the corners can be argued to cancel out. This blue bit here and the red bit there also cancel by asymmetry, by time translation. So we can forget about them. This horizon part is null, but it can be approached as a limit of a space-like surface. And so you can calculate this part using some limits as r approaches the horizon. And similarly for the extrinsic curvature here on the singularity, that's also finite. So there are really 3 non-trivial pieces. There's the piece from the horizon, the piece from the singularity, and the piece in the bulk. And together those 3 things add up to give you 2m for the action growth in every case that we looked at.
That's a coincidence? Is this some Hamilton-Jacobi like?
It's not Hamilton-Jacobi. That we understand, but it's not. It's not Hamilton-Jacobi.
Sorry, the place where this blue region ends, is that the singularity or the
It's the singularity here. So here in 3-dimensional bulk, the Penrose diagram is straight, but at higher dimensions it bends in some.
Does this work however bad the singularity is, or is there some? Could this rule out some kind of singularity because it's divergent?
That's a great question, which I will address at the end a little bit. We don't really have a full picture, but it seems like some field theories in the bulk are more sensitive to the singularity than others. But here it turned out to be finite. Okay. So that's the calculation that we performed. And so, for example, in the case of small, like Schwarzschild black holes, this is 0, this is small. So it all comes from the extrinsic curvature, in fact, on the singularity. Yeah.
You said the corners cancel?
Yeah.
But the extrinsic curvature jumps across the corners.
That's right. Those jumps cancel. That's the thing.
It comes. Did you say all the contribution comes from the extrinsic curvature turned out the singularity?
For the case of small.
For
small black holes, much smaller than the ABS radius.
And what happens for super ABS? Where's the?
Then all the pieces are
the
just some numbers, and they cancel to give you 2m. So there's some non-trivial cancellation between the 3 terms in the.
I see, but the extrinsic curvature of the singularity always has a serious.
Yeah, it does contribute. That's right. So here is the picture I promised Raphael. So here's the boundary time evolution we want to try to understand this, right? To have this tensor network picture of what's going on. So imagine this big blue, I already explained to you this network. I have this big blue unitary time evolution, which is the bare Hamiltonian evolution. Right? I'm applying the UV dynamics of the field theory.
So the blue things are supposed to be the boundary of ADS.
That's right, that's right. Yeah, so this is the spatial boundary, and then time on the boundary runs up like that. And so what we should really imagine, the picture that we want to advocate, is that you should think about this bare microscopic time evolution. It mostly doesn't do anything, right? Most of the degrees of freedom are not excited. Order entropy amount of degrees of freedom are excited, and they're rapidly processing their information, but nothing else happening. So what you want to kind of do is imagine passing this bare time evolution through the renormalization group part of the circuit and producing some renormalized time evolution which acts only on the low energy degrees of freedom. So this is kind of the picture we have in our mind when we say that the complexity growth should be some property of the sort of low energy physics. It doesn't depend on the fact that you have this complicated bare Hamiltonian here, because most of the degrees of freedom are not computing, they're not dynamically evolved. Instead we have some renormalized unitary transformation which acts on the small set of degrees of freedom that are thermalized. And it's the complexity of this part that we're calculating, the growth. And so, we have a picture where you sort of take this unitary part, and just like outside the horizon, the ground state was a sort of picture of the history of computation, the center was a picture of the history. We somehow imagine this blue part just gets sort of taken up into the wormhole, and then the wormhole was again a picture of computation that produced this complicated thermal double state from the simple state at t equals 0.
So the blue parts are now are the horizon.
Sorry, which ones? These or these?
The blue ones. So
Yeah,
that's on the horizon.
it looks like maybe the time evolution on the stretched horizon or something along those lines.
But are you then asserting that the blue parts, I'm supposed to think of that as gates that are built out of these sort of thermal...
Yes,
like,
exactly. The effect of passing through the unitary of the renormalization group part is that you get renormalized gates that act on your low energy degrees of freedom. Okay, so that's sort of the picture of how the complexity evolves in this state in terms of the tensor network language.
Sorry, so what happens if I consider a boundary region that's not fixed?
Oh, you mean when times run equal?
Yeah, if I change this boundary cut.
Yeah, so the action only depends on the sum of the two times.
If I'm not just shooting 2 times, but I'm shooting a more complicated...
Oh, you mean like you're...
Quasi surface, yeah.
Oh, you're varying in, like, time evolution in space, too. Oh, I don't... that's a good question. I haven't thought about that very much.
Because, like, if I choose the opposite time evolution, it doesn't grow the complexity. If you choose the same time evolution, it grows.
That's right.
How much it depends on this boundary.
So one thing which we have looked at is, like, localized shocks, which is sort of like this. And, it all works beautifully in that case. I don't have time to go into it, but yeah, so that's one step in this direction, but studying the full Cauchy problem, I don't think we've done that. So let me just mention charged black holes really quickly, and then I'll wrap up. So if you have a conserved charge, you might expect the dynamics is more constrained, so it should complexify more slowly. And so we expected that there would be some kind of modified bounds in the case of conserved charge. And so here, I'm not going to explain too much about how to think about this, but the idea would be that the relevant quantity is now not the energy, but the energy relative to the charge with chemical potential. This is what appears in a thermal field double state. And so the idea would be, in the case of some finite charge at fixed chemical potential, the complexity growth is bounded by not the difference in the energies, but the difference in n minus mu q relative to the ground state.
I'm confused.
Where
does mu come from?
Oh, mu is the chemical potential.
Yeah, but where did I get it?
Oh, I'm imagining I have some thermal, I have a black hole which is formed at some fixed chemical potential. I threw some charge in, or maybe it's in contact with the
You
environment.
put mu in and you calculate q.
Yeah.
But why don't I have to put a beta in to calculate n?
Yeah.
Well, I mean, beta is in there. It's just not in this formula.
Yeah, well, I guess the question is why does the chemical potential appear in this formula but not the temperature?
T would appear with the entropy. So this is like, isn't this like free energy minus TS?
Yes, this is somehow the TS part doesn't actually enter.
But this is like the Hamiltonian in the Gibbs distribution.
That's right. Yeah, it's like I'm just lumping the charge with the Hamiltonian, and then there's still the entropy part, and that never appears in either the uncharged or the charged case.
I think you just imagine that the two sides, that you've put some electrostatic potential on one side, which is positive, electrostatic potential on the other side, which is negative, and that causes the charge to lump up on one side.
Yeah.
And it's actually in the Hamiltonian.
That's right. That's right. Okay, so then we can check this bound in various places. One is rotating black holes in 3 dimensions, where the charge is angular momentum. You can calculate the rate of growth of action, and it's exactly equal up to a +1 from some funny business in ADS3. It's equal to the rate of growth of the action. So the bound is again saturated with no changing of the prefactor. The same for small charged black holes. With the same prefactor that worked for the uncharged case, the rate of action growth precisely saturates the bound that comes from calculating n minus mu.
So can you just, what does the ground state look like?
Well, so in both these cases, the ground state is just empty ADS.
So it's still just empty ADS,
Yeah.
so the potential doesn't.
But these are all statements about the action, not about complexity calculated independently.
Yeah, so here I'm just phrasing in terms of the action and saying it's consistent, assuming that CA thing is true, CA duality is true, it's consistent with the bound imposed on the complexity. So absolutely, you must assume that complexity equals action. Without that assumption, there's still an interesting result that these things are sort of universal, but there's this extra step.
No, but there are some independent arguments about why this might bound complexity.
Yeah, of course, yeah.
Could these please work in a time-dependent setting? So let's say you've got a collapsing black hole that's moving around. Is these statements still true?
Yeah.
Well, you should be proving them.
We calculate them for like a simple collapsing black hole, yeah.
It should be, if it's deep, it should be something just follow some Einstein's equations somehow. You shouldn't need to know the solution.
Yeah, I mean,
We think so.
yeah, that's right.
As a statement about the action, it's something that you can just.
That's right. That's
One
right.
of these rate
I mean, you're
equations
finding
type
something
of
very
things.
general about the action, maybe there's a simple way to get to that answer.
Yeah, that's right.
And whether or not we believe that that's complexity.
That's right. That's right.
Oh, so could you do it without the black holes entirely?
Yeah.
Just some dynamical space-time?
In principle, yeah. We haven't done that, but yeah.
Let me follow up on that. Is there a claim that you would make that the complexity for a reduced density matrix for some subregion is given in terms of something involved in the modern Hamiltonian?
Along the entanglement Hamiltonian.
Yeah. Your formula sounds very suggestive of that.
Yeah.
But in terms of action, there is no.
Well, I have a proposal for what action to compute.
Okay. Yeah.
No, I just mean if you look at action rather than Hamiltonian, it's the same action.
Yeah, maybe, okay, that's a very interesting question, but maybe we should defer since I'm already way over time. Right, now let me just mention one very puzzling case. So now let's look at large charged black holes, bigger than the ADS radius. If you go to the near extremal limit, so near zero temperature, this is what our proposed complexity bound said. It says that with this prefactor, that the complexity should grow no faster than the mass minus the extremal mass at the same charge. Okay. Now, calculate the action. What you find is that the action grows not like n minus mq, but like square root of n minus mq. So it appears in this case that if the action were really the complexity, and if the complexity obeyed this bound, then you can parametrically violate the bound in this case. That sounds bad. But there may be a way out. If there is a state in the spectrum of lower n minus mu q than the extremal black hole, in other words, if the extremal black hole is not the true ground state, it means that this calculation we did here is wrong. We're supposed to refer it to the ground state, not to some particular state in the spectrum. So this bound is not the right bound. It's something much bigger. And then maybe this action growth is consistent with that bound. And so this led us to conjecture that any black hole that violates the complexity bound has to be unstable, in the sense that there's a state of lower n minus mu q in the spectrum. So that's a conjecture, we can test it, and if it fails, then we're out the window with the bound, or with CA, one or the other. Yeah.
So when you say that's the conjecture you can test it may still be false in some effective theories of gravity and charge stuff, right? I mean, it could either be something that's manifest at the level of whatever effective action, or something that's a constraint on the effective action.
That's exactly right. So for example, here we were just considering Einstein-Maxwell theory. Maybe you could say that doesn't make any sense by itself. There's always a scalar field, and that scalar field would condense in this near horizon throat of the black hole. And then you get some other kind of black hole. And so there's plenty of independent reasons to believe that these black holes are unstable. And so this is just another perspective on that.
So you're talking independent theories.
Yeah.
I think as Simeon is saying, is an alternative statement of this weak gravity conjecture.
That's related, yes. Yes, that's right.
But I mean, which is it? I mean, you're saying there are independent reasons to think it should be unstable. You mean just in Einstein-Maxwell theory?
No. I just mean in the completions we know there are
Oh, in the completions
plenty of modes available to make it unstable. I don't mean it within Einstein-Maxwell. I have some other reason for thinking that it's unstable.
Well, because all the completions we know do satisfy the weak gravity conjecture.
That's right. Okay, so I'll wrap up. So I told you about complexity equals action and about action growth, and I tried to convince you that both of them were reasonable conjectures to make. And taken together, they imply that black holes are the fastest complexifiers in nature amongst some reasonable class of states. So a couple of things that are really interesting to think about, which we're thinking about right now, is, I guess, this issue of ground state complexity or thermal complexity. So I mentioned that the complexity of the ground state is UV divergent. The complexity of the thermal state relative to the ground state seems to be finite. So in other words, adding thermal correlations relative to the ground state makes sense independent of the UV cutoff. So that's a really interesting quantity to calculate. Another interesting question is, going back to this definition of complexity, is there really a natural continuum notion of complexity? Like, is there, for example, a natural value of K, of the K locality in the Hamiltonian? And one reason I think there might be is that many body operators tend to be highly irrelevant. So they don't affect the low energy dynamics. And so you might think that for a good continuum limit theory, maybe there's effectively few body operators in some appropriate sense that are important. So maybe there is actually a sort of effective notion of K that's valid more generally across some class of field theories. Okay, a lot of other things you can think about. But it was suggested by Lenny that I was going to solve all problems, so let me just comment on how that might happen. If black holes are going to be the fastest computers in nature, then there's some sense in which no part of the Hamiltonian can be wasted. Everything has to be working together with maximum possible efficiency. And so maybe that means all the parts have to work at their own physical limits. So perhaps from this meta principle that black holes are the fastest things that produce complexity, maybe that means all the parts have to also work in their own respectively complicated ways. So here's how it relates to shear viscosity. So this is the interproduction formula, which Sean wrote down. So if I divide by S, then I get eta over S here. And this is the derivative of log S. So maybe black holes want to like minimize or maximize their scrambling time when you shear them. Okay, thank you.
So can I apply this calculation to evaporating black hole in flat space? I mean,
I don't see why not.
So what happened during the evaporation? The complexity is keep growing?
Well, from the point of view of a semi-classical like thing, it's just going to be slowly decreasing the mass, right?
Yeah. So the complexity is still increasing.
It'll increase, it'll just increase at a decreasingly slower rate. That's my expectation.
Are you anchoring the boundary at some finite radius point or something? Like in flat space, naively, there's none of this patch business.
Yeah, that's a good point.
What was the point?
Sorry, what's the point?
About where we're anchoring.
If this anchor on spike
You might want to put like a surface, like somewhere a little bit outside the black hole and anchor there. Like anchor at 3M or something and then evolve.
There's no reason. Then they really need to give a boundary.
That's right. It's more complicated, but there is an issue. Like if you look at the Schwarzschild black hole, and the small black hole, then it doesn't evolve for a long time when you anchor it way out the boundary. So there is some confusion there. Yeah.
Let me go back to this no black hole case. So if you have pure ADS, complexity is just constant.
Right, the patch just goes up.
Because it really is time translation in that.
Yeah.
So the statement would be, if you have a horizon, no matter how dynamical it is, then that space-time saturates the bound. I mean, clearly it's not all space-time, so because ADS doesn't.
Yeah, I mean, yeah, it depends on the properties of the black hole, like if it's charged or so forth. But yeah, if you had an uncharged black hole and it was more or less in equilibrium, then yeah, I would think the expectation would be that it saturates this bound.
Otherwise, it also saturates it in empty ADS, right? It's just
No, because it's
mass
just
is zero,
constant.
right?
because
Yeah,
the mass
mass
is zero.
so.
What was the question?
Thank you. Okay. Okay. Okay.
Yeah, in PADS nothing happens.
Yeah, and then it does saturate.
And it's nothing happens, saturates
Yeah, it
zero.
does, but-
Yeah,
Okay.
that's
It
right.
wouldn't saturate the bound if you had a star in ADS or something.
Probably.
Yeah, so yeah, like one thing you can do, for example, is take these black holes and put a static shell outside of them, which takes up some of the mass, and assuming that shell doesn't compute, then you get something which is strictly lower than the bound, because part of the mass is just stuck in the shell. There's also a time dilation effect. So that's one example of making a perturbation where you put some of the mass in some possibly complexifying, but not nearly as rapidly as the black hole, and then you're
The
very...
black hole in the shell relates to the question of the instability of the, taken from superconducting.
That's right. Yeah, like in this extremal, in the near extremal large black hole, one instability would be that you have some scalar field which can condense. And then there's some hair outside the horizon, and that hair is like a kind of shell that doesn't compute.
If I naively think about some horizon in the theta space, then I conclude that this complexity is decreasing for each such region.
Decreasing.
Because this horizon is like shrinking when you move to the future.
No, it's not.
No, yeah. Yeah, let's start with this offline. Yeah.
I mean, a striking aspect of this is it calls out actually a significant role for the singularity.
Yes.
Some boundary process, which I think is sort of new.
Yeah.
So,
And so in particular, like we've looked at, for example, theories we have at dilaton as well.
yeah.
And there, the dilaton runs large in the appropriate direction, and so something happening in the singularity, and there's some. It seems like you need to know about the physics there to say something. So it does seem like it's probing the singularity in an interesting way.
I mean, I've asked you about higher derivative things, but even at the level of Einstein gravity, I don't know, well, there's people here that know this much better than me, but even in Einstein gravity, if you imagine a small perturbation of a Schwarzschild black hole, aren't there these Kolotnikov-Lifshitz modes that grow as you get to the singularity, where you might imagine a small perturbation that you might think shouldn't do much to the complexity.
Yeah.
It wouldn't on this tensor network.
Yeah.
Thing. I mean, those perturbations might grow right up at the singularity within a Planck length, the singularity, and
You're worried with the extrinsic curvature term? I mean, the bulk term will be fine just because of what Einstein's equations are.
Yeah.
Right, I'm worried about the extrinsic term.
Yeah.
Now maybe there, on this, because of the magic of the whatever underlies your result, it cancels out.
Maybe.
But I don't think you have to worry about plunking distances in this.
Why not?
You can cut off. You won't make practically no mistake at all if you cut off things at a classical distance, which is a small fraction of the ABS radius.
Well, but suppose there's a mode that's getting large.
What's that?
Suppose there's a mode that's getting large.
No, that's not what I'm saying. I'm saying it's not a plunking issue. I can make my cutoff, let's say, at 1/10,000th of the ABS radius, which is a classical distance, and I won't make much error.
But
Well,
this
in your
makes
setting,
sense.
what if you don't make
your
a
setting?
cutoff?
But
this makes
if
no
you have
sense.
some
It's-
if you have some mixed master universe going
I
on
understand.
there.
I'm just saying it's not a plunking issue.
Yeah, but the question is whether it's really still true in that setting.
Yeah.
It's whether it's cutoff sensitive.
Yeah, I mean, I
on
think
that number.
Yeah, but it's not a plunking.
Okay, but you call your cutoff L or
Absolutely.
whatever, whether it's sensitive to
Yeah,
L.
so-
I'm saying it's something that can be answered classically.
Yeah, exactly. You're right.
Yeah.
Can I add to this?
Yeah.
In the beginning I asked, are you taking classical action and inserting solution of classical equation of motion, and then you're, whatever you get, you
Yes.
start talking about tensor networks and what it means. Or you're doing something else on GR side. You just take classical action, classical solution, and compute.
We're doing both things. I mean, we did a calculation in classical gravity of the classical action
Yes.
on the classical solution.
Yes.
And
But
we are
then-
trying to interpret that in
But
terms
then
of...
you try to use these without anything about quantum correction or the fact that you have singularity and horizon. You're not changing this space-time picture,
That's right.
and you're saying, now here are tensor networks, and I would like to understand their properties of states.
I guess
What exactly are you doing after you finish the GR part?
what I would say, I put it this way, the GR is a definite calculation,
Yes.
and we would like to try to interpret the outcome of that calculation in terms of tensor network. That's the
But
perspective
you
I
are
was
not
taking.
changing anything about the concept of horizon or
No, the
singularity.
calculate, nothing about the geometry has
Because you're-
changed. It's the classical action, classical solution, same geometry, singularity, all that stuff.
Mhm.
So let me understand. So put the cutoff at some distance L, with that 10,000th of the ADS scale. So the contribution of this extrinsic curvature term is L independent on the standard Schwarzschild solutions or whatever family of solutions you want to look at. So if you have some perturbation that's growing toward singularity, the worry is that the contribution might grow with whatever is L goes to zero.
No,
Yeah, how do these Koloknikov-Lifshitz things work?
I don't know.
Actually, I think,
Do you know how? Or,
They're chaotic, man.
They're chaotic, but don't the amplitudes grow, the derivatives
You
grow?
have to change because he takes
Yeah, I think
a
the derivative.
static solution.
yeah, certainly.
No,
it'll be a
I'm asking
different
about,
solution.
I'm asking
You
about a
have to-
perturbation
chaotic,
around.
You have to make an anisotropic solution.
I'm
Yeah,
asking about a perturbation
And
around.
he didn't do it. This is where
Yeah,
are
but the
you
question is,
using
am
a
I-
classical static solution? So you can't see
instabilities
how-
inside
I'm going beyond what they describe.
It better
I'm
still
asking
makes
about
sense
how
if
to
you don't
perturb
use
the
it.
formula.
Yeah, it better still makes sense if you don't use a highly symmetric solution.
actually,
It has to make sense
more dramatic
beyond that.
instability inside the horizon. This charge.
Of course you do. And the question is
You
whether
mean the
you'll
inner,
still
you're
use
talking
it.
about the inner.
yeah, the
Yeah,
horizon is also an
But
interesting
did
place.
you,
So in
Did
fact,
you-
these cases that don't work for you, it may be that it's because inside the horizon doesn't look like what you think it does.
We explore that idea a
We
little
don't
bit,
think that's what's going on.
but
That doesn't.
The wheel with patch never reaches inside the inner horizon. It gets close to the inner horizon, but it never reaches inside it. So, depending on how, if the instability was just a null instability at the inner horizon, that wouldn't affect us at all. If it actually made it a space-like inner horizon, then it could affect us.
I thought the belief was that the singularity becomes space-like or something at the end of the day.
Yeah,
It's not there, that's actually true.
that's a possibility, certainly. At the very,
Then you would hit it. But
yes, you would.
Right, and that would change your answer.
It would, that's right.
Well, it might.
Well, it would definitely change it,
Yeah,
but,
so we change it.
well, I mean, unless we got really unlucky, but rather would resolve the problems. But, I mean, there's an issue about whether the horizon moves in a lot or a little, like a Planckian amount or some macroscopic amount, then maybe it does or does not affect
Well,
very much the
if we're
action.
just talking about the effect, no effect of external perturbations,
Yes,
just the effect of quantum fluctuations, and it's still believed it makes a space-like singularity,
yes.
but that space-like singularity would be very close to where you put the original inner horizon. So it would be almost like. And then I don't think it would change anything. But you
Yeah.
could ask what happens if you actually do make external perturbations, and,
Well, and so, for example, in these Einstein-Maxwell dilettante theories, there is a space-like singularity. And, yeah, so it's different for those charged black holes.
I think we should thank Brian again.
Thank you.
That's a real question.
Yeah, no, I agree.